Thank you, everyone, for joining, and I'm very happy, to have this opportunity of presenting at this PyData Global Conference. So, the topic of today's session is exploring tools for machine learning, interpretability. Here's a brief outline of the talk. So I will give a brief introduction about what we want to do today. We're actually going to see many of these techniques in a concrete example. So I'm going to describe the data set. Then we're going to feed a couple of models on which we're going to try to understand how they generate predictions and how features interact with each other. The aim of this talk is not to really focus on the model fitting, but to try to see later in the process how one can actually, let's say, look into them, into how they create predictions. At the very end, I will leave some reference, which I will then share on Slack and also on social media if you're interested. So in general, we would like we want to understand what our machine learning algorithms do. That's very crucial. It's important in order to understand the limitation and to understand the scope and the potential effect that they can have. So that's why this topic is becoming very, very popular these days. And actually, this is a huge area, and what I'm going to do today is just look into the surface of the problem. But before going into this type of techniques, we need to take a step back and really emphasize that what is really important, it's really to understand the data and the problem. So even before fitting an algorithm, we must understand the context of the problem that we're trying to solve. Secondly, we need to understand the input data, the sources, the biases, and the limitations, because that's definitely going to impact the way the machine algorithm outputs predictions. And last but not least, I would argue that in spite of the fact that models are becoming more complex, we need to understand the logic behind the algorithms. For example, the difference between a linear model and a tree-based model. So again, what we're going to do today is to go to a very specific use case on which we can see some of these tools for kind of model-dependent and model-agnostic methods in action. So this talk is based on a blog post that I wrote, so you can follow all of the code and all of the comments already online. I just want to mention that, this was motivated by the work of Christoph Molnar on his very nice book on interpretable machine learning. Actually, the data set I took from there, but the model that we're going to look into are a little bit different from that sort of reference. And I also want to mention the book of Serg Masís, which is about the Python implementations. A remark that I want to mention, and I don't have the time and it's not of the scope of this talk, is that interpretable machine learning is not equivalent to causality, because these are slightly different problems, and in the references below, I share some very nice articles about this subject. Okay, let's go into the concrete use case. So this probably is a known data set. So what we try to predict here is the count of rented bikes over time. So this is a glimpse of how our pandas data frame would look. Our target variable is the CNT, which is denotes counts, and it's integers and positive value. And we have two types of predictors in this data set. So we have seasonality predictors, for example, the year, the month, the week of the day of the week. We have daily data. This is approximately 2 years of data. And we also have temperature, humidity, and wind speed features, which are more methodological, which we can assume that at prediction time, we can get them from a forecast provider, so to say. So, the objective is to generate predictions for this time series. So let us take a glimpse into how these regressors look like. So again, it's important to do at least a small EDA before going into the model fit. So the black line denotes the target variable. And what we can see is that there's a seasonality pattern that repeats roughly every year. And there's a slight trait component. So the first blue curve denotes the temperature. So it seems that temperature could be a very good regressor for explaining the seasonality, although they don't match completely because, day 200, so to say, the target variable is a little bit flat while the temperature peaks a little bit. Yeah, something that I actually forgot to mention is that in our data set, we also, let me go back, we also have a variable called days since 2011, which is essentially a growing variable. It's a linear trend. Okay. Yeah, so humidity and wind speed, although they don't have a trend, they could potentially explain the fluctuations, let's say, within each week. Yeah, and day since 2011 is just a linear trend, so it's an artificial variable, which is it could be helpful for prediction. And also we have the year variable, which is in this case is nothing else as a step function, which could also help us to predict, for example, this kind of growth in the amplitude of the seasonality. In this plot, we also see how the seasonal features actually work. So here I'm plotting the distribution of the count variable across different type of categories. So for example, we see that in general, we have summer and fall, a higher byte count on average than, for example, some days in the winter. Well, so we clearly see that on the monthly seasonality. We also have some tags about whether it's a holiday or not, and we also have like an indicator on kind of whether the weather is good or not that good. And it seems that when there's bad weather, people don't rent bikes that much. So we could argue that these features are relevant, and maybe it's a little bit challenging to add them all at the same time. But just for this exercise, I want to leave them all in the model to try to see how the model uses these kind of correlated predictors. So for this simple exercise, we're going to do a very simple train test split of our time series. So the black line, it's going to take like 1 year and a half of training data, and we're going to test a couple of algorithms, let's say out of sample in this red line, which is the very last end of 2012. Again, it's very important that as we are working with time series, we can just not randomly shuffle the data. So about the modelings that we're going to have. So I selected 3 types of models, which represents 2 types of different flavors. One is a linear model, which is actually taking all of these features and put it into the linear regression. But I also added second order polynomial interactions just to make sure that we might have to control for non-linear kind of effects. But then as I'm having all of these combinations, I also don't want to overfit. So for that, I'm running a cross-validation, like a time-slice cross-validation step with a lasso regression so that I can do certain variable selection. So it's really a little bit of feature engineering. The second model, on the other hand, is just a gradient boost model, in this case, just XGBoost. Here you can see the scalar pipelines. So we haven't done anything fancy, maybe 2 comments. So for the categorical variables, we use a one-hot encoder for both models, and for the linear models, we scale the numerical variables. And what we want to see is how these models perform and try to understand how they generate predictions. So let us look into the out-of-sample performance. So on the left-hand side, you see the in-sample performance, let's say in the training data, and the right-hand side, we see the out-of-sample predictions. So in sample, it seems that the gradient boost model is doing a little bit better. You see that the distribution of the errors, which are in the lower part, a little bit shrink. In the upper part, we see the true against the predictions. But out of sample, actually, we could argue that these models are relatively the same. We can explicitly look into the out of sample predictions. And again, we don't want to fit the best model, but at least they are quite comparable. So what we want to do next is to understand how these predictions are made, because again, these are 2 different types of models, and whether we want to try to understand if there are any type of consistencies or differences between them. All right, so let us start with a model kind of dependent way of looking into it. So without going into anything fancy, if you have a linear model, you have something very explicit to look into once you fit the model. So again, for a linear model, it's just a linear combinations of features that are weighted by what we call the beta coefficients. So in this table, you see, let's say I rank the beta coefficients, also in absolute value. And this is okay because we scale the variable. So I mean, the scales will be somehow comparable. And it's interesting to see that the most important variable with respect to this kind of ranking of the beta coefficients is the interaction between the month of July and temperature, which actually is negative. So what would expect that, or let's say what we think at first glance, that in July, this coefficient might be positive. But again, we need to understand that the beta coefficients need to be understood by controlling the other variables. So in spite of the fact that this is negative, notice that the coefficient for the temperature and for the month of July are positive, and actually quite positive. So what it could be, or like my intuition says that even though that in July we have a high temperature, maybe while controlling for that, maybe July actually has is not giving any additional information, and actually could be explaining the fact that our target variable is rather flat close to July, where the temperature peaks a bit. So reading this beta coefficient when there are interactions is actually not straightforward, but it's a good place to start, and it's definitely something which I recommend looking into it. But something that can give us a little bit more information is by looking into what we call the weight effects. So the weight effect is nothing else than taking the beta coefficients and multiplying this by each data instance. So we can see the distribution of each feature across all the complete data set. So, for example, the categorical variables, you see that we have a lot of variables, let's say, centered at 0 or weight effect at 0, and then at a certain value, again, because this is a dummy encoding. And if you also see the temperature like ranges across like a continuous spectrum of the weight effects. On the orange plot, we have just the linear features, because we have many features in this model. And in the green one, we have the features which have a highest beta coefficient, which could include interactions. So if you think about whether a variable is important, notice that, for example, the month of July times temperature seems to be having the highest beta coefficient, but for a lot of these data instances, this is actually 0, meaning when the month is not July. So it is important with respect to beta coefficient, but it's impactful across all the data set. Whether the temperature, it's something that it's kind of always there. So one way of capturing this intuition is to take, or like look into the ranking obtained by taking the absolute value of this weight effect and then taking the average. So in this case, a temperature becomes quite important and goes high up in the rank. And then we have the trend component, which is the days since 2011, as the second one. And so I guess the intuition here is that like these two variables could explain a lot of variance by explaining, on the one hand side, the seasonality with the temperature and the trend component with just these days since 2011. I guess with interaction with the year. And maybe going down into the rank, this could explain the fluctuations which are not captured by, let's say, by this kind of model with two variables that we could potentially fit. Actually, the weight effects can also be interesting to understand interaction. So before going into interaction example, let us go into a specific plot where we have just one feature. So we can here plot the temperature as the weight effect as a function of the temperature. So it's no surprise that this is a straight line, because again, this is just the linear component. And the color here denotes the weight effect. So what we're looking into is that the temperature has a positive effect on average on the bike count. So when it's warmer, people probably would like to go out more. Where the temperature is actually negative, this is actually affects the prediction into like, or going into negative contribution. But then we can do the same game with two features. So here we have the temperature on the x-axis and humidity on the y-axis, and then we color code by the weight effect, which is just adding the contribution of these two features plus their interaction. So what we could see here, for example, is that the weight effect that we have at prediction time, as for example, 10 degrees and humidity 40, it's comparable to what we could get at 20 degrees, but with higher humidity. And by looking into this kind of plot, we could see how variables interact with each other. So it's even for linear model, this is super useful. Moreover, we don't need to go into just the aggregate feature importance, but we could actually, with the linear model, go very deep into looking into how predictions are generated for a specific data instance. So in Molnar's book, they take exactly these 284 features, so that's the index in the data frame, and here we see the decomposition of the prediction against the feature. So for this specific case, this is a very bad day, probably raining, and it was in October. So for this specific feature, what is driving the prediction more is the indicator variable of the weather condition. We have all of the relevant variables in red, and in purple, we just have the linear terms just to compare. So it's very, very transparent how linear models generate predictions. On the other hand, XGBoost or tree-based models also have a very kind of clear intuition of what's happening, although disentangling the effect is a little bit trickier. So I don't want to go into details, but these tree-based models have inherent measures of importance, which roughly want to encode, let's say, how the features are selected while branching the sequence of trees. So here I have the rank of some of these metrics. I don't want to go into detail, but it seems that by ranking them, we see that temperature and the strength component are also very important for this model. And yeah, other meteorological variables like the wind speed, humidity could also contribute. So comparing these two types of models can now be a little bit difficult, because on the one hand side, we have beta coefficients, and on the other hand, we have this kind of tree like inherit metrics. So now we want to go into the direction of model agnostic methods. So there are many of them, and I just selected the ones which are maybe a little bit easier to understand. But again, this is a huge field. So the first thing that I want to study is what I call partial dependency plots. So the idea here is to try to understand the effect of a specific feature into a target variable by marginalizing it over the whole data set. So very specifically, for a concrete example, if we have a fitted model, which we don't care what it is, and we call it f hat, and we want to compute the effect of, let's say, temperature, what we could do is for each value of temperature, in this example, temperature equals 8 degrees, we can take the average over the whole data set, where we replace the temperature feature with a fixed value, in this case 8. So this will give us just a single number, and then can do this for the grid of ranges of temperature of interest. I can do something similar, but instead of averaging over the whole data set, I can do this at data instance level. So in this case, I will get what is called individual conditional expectation curves. So as a side remark, maybe to wrap this up, if I take the average of this ICE plot, I should get the PDP plot. So let us take a look into how this look for this specific use case. So in these three plots, I show the partial dependency plots for three features: temperature, humidity, and wind speed. And yeah, the y-axis it denotes the count, so we want to understand the effect. So the blue line denotes the linear model, and the orange line is the tree-based model. So one first thing that we see is that for humidity and wind speed, there's not much difference. They look pretty similar, but we see two different things in that temperature. So the both lines, which are the partial dependency plots, look a little bit interesting. So for the linear model, we get a linear relation, again saying that higher temperature implies higher bike count, but the tree model actually understands that at some point there's a saturation effect on which temperature above 25 degrees actually decrease the number of bikes. And this could also make sense thinking about the data set. Another important difference is the fact that you would expect that the IC plots for the temperature will always go up, let's say with a positive slope, because I guess that's the beta coefficient that you learn. But you still see these downward curves which have negative slope. What could this be? Well, this is actually an effect of the interaction. So we can capture interaction effects via these ICE plots, which are often hidden when you do the average. So looking into this type of line, this could come from data instances on which we have the month of July, and the overall contribution with this very negative beta coefficient make this go down. So these plots are really helpful into how to understand our model, but they have a big limitation, and it's the fact that if you have higher correlated variables, then these results can be misleading. Why? Well, if you look into how this is computed, if, for example, you take temperature equals to 25, and then you have in your seasonal variable that the month is December, this is not really representative of the data distribution. So you're going to test this and generate these plots with data instances which are not really relevant or, let's say, physically real. So bear that in mind whenever you're working with partial dependency plots. We can also see an example in 2 dimensions. So I don't want to go into details. But the only thing that I want to remark here is that for wind speed and humidity, these partial dependency curves in this case are not straight but a little bit curved, and that also the effect of the interaction effect. So you could see in the bar in the box below where you have the beta coefficient, that the beta coefficient of this interaction is the highest among these two. So this you can also do for 2-dimensional plots. Another natural measure of importance is what we call permutation importance. And what we do here is essentially for each feature, we shuffle the data instances and then test the accuracy once this is shuffled. And what's the intuition behind it? Well, if a feature is important for your model, if I shuffle the values of that feature, the accuracy must go down. Whereas if the feature is not that important and I shuffle the values, then it shouldn't change that much. So it's clear that this is quite natural, and it's interesting to see that again the trend component and temperature are always in the top. So that's where all these models agree. But for example, the seasonality and humidity don't rank the same. I must say that this measure of importance also suffers from the fact that whenever you have the correlated variables, you might be testing the accuracy on points which are not physically relevant, so to say. And so that I often recommend, or like in the literature, they often recommend when presenting results on partial dependency plots or permutation importance, also present the corresponding correlation matrix, or maybe a dendrogram with the correlations, because it could happen that highly correlated variables actually can kind of split their importance, and they might look low in the rank. So last but not least, I want to talk about SHAP values, which is again a very huge topic in an area of where there's a lot of development, but it's also quite nice to understand how models generate predictions. So I'm going to give you the recipe super fast, so to say. I know there are other talks on the subject, so maybe you can look into depth. But let me go through the idea. So the main idea of SHAP values is to consider features as teams playing a game where they're competing to increase the accuracy, so to say. And what is important is that we cannot weight all of teams at the same time if the team at the same weight, so to say, if they have different number of team members. So SHAP values actually it's not a ranking for features, but I can generate a SHAP value for each data instance. So for simplicity, let us assume that our count model has only 3 features: temperature, humidity, and wind speed. And we're going to compute the SHAP value for this specific data instance, and we have 15, 16, and 14. So the first thing that I do is I sample a coalition, meaning a team. So it's a subset of these features. And let us assume that I just take temperature and humidity. Then I want to generate predictions with a fitted model. This is what I call set prime. And in order to generate predictions, I use my fitted model with those values, but with the features which are not part of the coalition, I just randomly change the value. So wind speed, I'll change that to 11. And let us assume that this prediction from this model is 4,000. Then I need to compute certain combinatorial weight, which is just depends on the size of the coalition, in this case 2, with regards to the total number of coalitions possible. Again, this is not super important. It's just a way to make this competition fair. And once I have this weight, which in this case is 1/3, I can fit a weighted linear regression. which the coefficients are going to be exactly the SHAP values. And where's the linear regression coming from? Well, we had just generated the data from this kind of recipe. So the target variable is going to be the prediction. So in this case, 4,000. I have an intercept, and then I have an indicator function on whether the feature appeared or not in this collision. So in this case, I have two coefficients like phi temp and phi humidity, plus an error. And if I sample for many collisions, then this will generate a data set with 3 variables or 4 with the intercept, and I can fit that and give the coefficient, which is in this case, we're going to be 5. So this is how the results look. So these are very nice, like the SHAP package has a really nice visualization component. So we see each kind of the top features plot, and here we see all data instances. So it's really, it gives a relation to the weight effects plots that I showed you before. The color of the points actually represent whether this has a positive or negative impact with respect to the target variable. So for example, for both models, the temperature has a kind of higher temperature, have a higher impact on the byte count, although for the tree-based model, it's a little bit fuzzy. And I think that we will see that in a bit. Notice that with respect to the ranking, the month of July times temperature comes quite up, but also temperature. So what we're seeing is that these SHAP plots, or like the SHAP value importance, is actually taking a little bit from the beta coefficient and also taking a little bit from the weight effects. And also in the tree-based model, we see that this actually coincides well with the features obtained by the XGBoost metrics. I should say that the algorithm that I explained before is really about, let's say, model agnostic, but there are implementations which can speed up the process, again, because there are a lot of computations to be done, which are model dependent. They should be very comparable, and that's why I'm tagging that with linear SHAP and tree SHAP, which are variants of this initial kernel SHAP algorithm that I briefly discussed in this slide. Yeah, by taking absolute values of the SHAP values, we can get like these ranking plots, which I briefly mentioned that before, so I want to skip this. But also something interesting is that we can generate also this type of feature specific plots on which we can see what's the effect of the temperature onto the SHAP values. And it's interesting to see that for the linear model, we get like a straight line, and this should be compared with the weight effect plot. And the temperature has also this saturation effect. So again, at temperature higher than 25, the effect of the temperature, of high temperatures, actually hurts the byte counts, and that explains why in the SHAP plots the color of the points, like blue and red, are a little bit kind of mixed, whereas in the linear model the gradient is very, very smooth. Yeah, last thing that I want to comment is that we can actually go with SHAP values at observation level. So this is how kind of this cascade plot or like waterfall plots look for observation 284. Yeah, we also see that the main driver of this prediction is the weather condition. And it has a negative effect. I should warn that this could it might be that this could be misinterpreted, because again, SHAP values are not really looking into the effect of the prediction, but actually on the average prediction on the whole data set. So my final recommendation here is that please take a look into the construction of the SHAP value. There's very nice documentation, because although they are very powerful tool, they can often be a little bit misleading when reading these results. Yeah. I hope this exercise was fun. I'm gonna share a lot of this reference where you can see all of the sources tied to each of the slides. And yeah, thank you very much. That's what I wanted to share with you today.
Thank you so much, Juan. Thank you so much. I'm certain everyone has learned more about exploring tools for interpretable machine learning. We have a question here from Ian. Ian asks, which is most useful? I'm assuming.
Yeah, actually, I think this exercise of looking how predictions are generated, should be kind of essential in the machine learning lifecycle project. So I think you should see all of them, and they're not hard to implement. There are many libraries which just make use a feed algorithm and generate these plots for you. So I would say, let's say, more like a detective, try to look hints, and each type of approach has its own limitations, but also gives you a little bit of information. So if you have something which is more independent, I will definitely go there. I mean, for linear models, definitely look into the weight effects and the beta coefficients. If you have more complex models, also SHAP values could be a very nice solution. And again, this is a huge field, and this is just a subset of methods that are out there.
All right, thank you so much, Juan. And here we have a comment from Ignacio. He actually commented during the presentation. He says, well, the series patterns are different in train and test sets, and it could be expected.
Yeah, I mean, this is I did that on purpose, so to say. So the time split, it's a little bit aggressive, but maybe in reality you will have something that you pull something in production, you do some analysis, but it could be that the data is or the model drifts. But maybe by looking into this type of plot and maybe tracking these values can give you information about whether your assumptions on the modeling phase actually hold when this thing is still deployed. And I think there was talk about interpretable machine learning at scale, which could maybe have touched on these points.
I don't see any more questions here. Just people asking for the slides and just commenting on the presentation. So thank you so much.
All right, thank you. Bye-bye.